Verse 3, lesson 16 and 17. 16, we're talking about irrational numbers. So your goal is to be able to approximate the value of square roots, see if you know what irrational numbers are compared to just rational numbers, and compare and order rational and irrational numbers. So big thing here is, which number is irrational? Well, if we're thinking about the definition of an irrational number, that is a number which goes on forever and ever and ever without repeating itself. So the question is something like, I don't know, pi irrational? And you would say yes, because pi goes on forever and ever without repeating itself. How about something like 0.3 repeating? Well, in its name we say it's 0.3 repeating, which even though it goes on forever and ever, it repeats itself. So no, 0.3 is not irrational. It is a rational number because this can be shown as a fraction, 1/3. So if we look at our square roots, a lot of times we have square roots as being irrational numbers, things like square root of 2, square root of 3, square root of 5. But the question is, out of these four, which ones are irrational? We have root 0, root 4, root 8, and root 16. Well, let's see if we can simplify any of these. The square root of 0. Well, that means that I am looking for a number times itself that gives me 0. Well, that would mean that 0 times 0 is 0. So the square root of 0 is 0. How about the square root of 4? And you will say, well, 2 times 2 equals 4, so the square root of 4 is 2. The square root of 8. Well, I know that 2 times 2 is 4, 3 times 3 is 9, but there's nothing times itself that's a whole number that gives me the square root of 8. Let's skip over that one and come back. Square root of 16, you can say, well, 4 times 4 is 16, so the square root of 4 is 4. All of these that come out to a whole number, 0, 2, and 4, those are rational numbers. Rational numbers, because all of these can be shown as fractions. We could do 0 over 1, 2 over 1, and 4 over 1. The only one that's irrational is the square root of 8, because it cannot be shown as a whole number. It's going to be a decimal, and that decimal is going to go on forever and ever. Okay, so let's try to order some of these numbers from least to greatest. Well, whenever I look at a list of numbers like this, I'm going to see, is there a negative number? And in this list there is not. So I say, well, then 0 is my smallest. Then I say, okay, is there something from 0 to 1? And we see, okay, 2, no. Square root of 5, we'll come back to that. But I don't think it's got to be greater than 1. 3, 1.2, 1, 5/9 is our next one. 5/9, because that is smaller than 1. So 0 and 5/9 have been ordered. 1 is next. Then we think, okay, now I need to start thinking about that square root of 5. And if I were to think about it, I'd say, well, it's got to be bigger than the square root of 4, but smaller than the square root of 9. And you might be thinking, why did I choose those numbers? Those are kind of random. Well, it's because I know that this equals 2 and this equals 3. So that on a number line, I know that the square root of 5 comes between 2 and 3. Now, is it closer to 2 or closer to 3? Well, since 5 comes right after 4, I would say it would be closer to 2. There's quite a bit of space between these numbers, so it would be closer to 2. So now I can order the rest of them saying, well, I know it's bigger than 2, so 1.2 comes next. And then my number 2, the square root of 5, and then 3. And we have our list. Okay, so being able to compare these square roots, figure out what two numbers are they between. And in this case, I looked at the perfect squares 4 and 9, because those will give me whole numbers on my number line that I can then order the square root of 5. All right, the area of this square is 2 centimeters square. What's the length of each side, right? Both the approximate answer and the exact answer. Well, if the area is equal to 2, that means I need something times itself giving me 2. Because this is a square, that means that the side lengths have to be the same, so something times itself has to equal 2. Well, if I do something like 1 times 1, that equals just 1. So that's not going to work. 2 times 2, well, that gives me 4, so that's already too big. I know that it has to be something between 1 and 2 for my side lengths. Well, the thing is, since we're talking about irrational numbers, guess what? The answer is going to be an irrational number. And if we think about taking the area, well, that means that I have a side times a side equaling 2, right? Side length times side length would give me the area of 2. Well, that's just side squared. Well, if I want to know what just one side length is, I need to get rid of that squared. And the only way to do it is doing the opposite of squaring something, which is square rooting something. So we would say, all right, s squared square rooted is just s because I got rid of that exponent, and the square root of 2. That doesn't have a whole number answer, so I would just say my side length is the square root of 2. This is actually the exact answer. The square root of 2 and the square root of 2. This is a number that goes on forever and ever, so by showing it in this form, the square root of 2, that's actually the exact answer. But to approximate it, I would say, okay, is it closer to 1 or is it closer to 2? Because I know it's going to be between those two. And I would say it's probably closer to 1. Okay, maybe I try something like 1.2 times 1.2, seeing if we can get closest with tenths. And that comes out to 1.44, so not super close. Maybe 1.3 times 1.3, which gives me 1.69. I think I can get closer. And I can, with 1.4 and 1.4 gives me 1.96, which is pretty darn close to 2. If we go to 1.5 times 1.5, that gives me 2.25, which is not as close as 1.4. So my approximate answer is 1.4. The exact is the square root of 2. The approximate is 1.4. So this is one way to think about it. Thinking about if I have side lengths squared, I would need to undo that to get the square root of 2. Another way to think about it, okay, so I'll give myself some space. Another way to think about it is relating it to some different examples that we do know, okay? Things like maybe we don't have the area of 2 anymore, and I have a different area. Maybe I have the area of 100. Well, if I use this same idea, that would mean that that is the square root of 100 times the square root of 100. Now you already know that if I have a square that has an area of 100, it would mean I would have 10 times 10. Well, that's exactly what we have. We have the square root of 100, which is 10, and the square root of 100, which is 10. Let's see if it works for another one. Okay, let's see that if the area is 36, then I would say, well, that's the square root of 36 times the square root of 36. Okay, just like we did with the last one. Area of 2, so it's root 2 times root 2. Well, that works because that's just 6 times 6. So when we get to our area of 2, that's just the square root of 2 times the square root of 2. Okay, and one way that I can actually check myself is when we have radicals multiplied together, we can multiply the insides together, the radicands, to get the square root of 4. And we know that the square root of 4 is 2. So that works. Our side lengths are the square root of 2 and the square root of 2. So a couple different ways to go about that one. Okay, these are some good examples that you can try, especially these squares down here if you had trouble with that, finding the side lengths. This one's going to be a whole number, and think about maybe this one not being a whole number. Maybe it's an irrational number. So if you want to practice, here's some extra problems. And let's go on to lesson 17, rounding and estimating. This is going to be pretty quick, because rounding numbers to a given place value and estimating measures is something that we've been practicing for a long time, many years. What are the rules for rounding? Well, there's a little saying that a lot of people have learned, and it's 5 or more, raise the score, 4 or less, let it rest. Meaning that if we are looking at something, maybe 3.652, and we say, I want to round it to the nearest tenth, what I like to do is put a line between my tenths place and all of the other places because I just want to see that tenths place. That's what I'm looking for. But I look to the right and see this 5 here. And it says 5 or more, raise the score. So I'm going to have to raise this 6 to 3.7. But if we have another example like 3.632, and I still want to round to the tenths place, I look at that hundredths, that 3, and say, well, 4 or less, let it rest. So I actually don't do anything. I say it's just 3.6. I don't round it down to 3.5. I just leave it at 3.6. So when we look at these examples, round 1,481,362 to the nearest 100,000. Well, I would say my 100,000ths place is this 4 right here. Okay, so I look to the right and I see an 8, which means that I need to raise this so that I have 1,500,000. Or round 3.14159 to the nearest hundredth. Well, that means that I cut it off right here and I look to the right. Look at this 1. And it tells me to let it rest. Leave it as 3.14. Okay? So, 5 or more, raise the score. 4 or less, let it rest. So when we see things like this, 13 and 5/12, I might think to myself, well, that 5 is telling me that I need to raise the score to the nearest whole number. But when we actually think about this, 5/12 is not bigger than half. That's what our rounding rules tell us is if we have bigger than half, we need to raise the score. But in this case, I don't. I would need to see a number that's 6/12 or 7/12 or so on. But 5/12 isn't big enough for me to actually raise the score, so I leave it at 13. I let it rest. Whereas with this one, when I look to the right, I see a 5, and it's actually a decimal 5, and so I raise the score to 14. So don't be fooled. If you see a 5 in a fraction, it doesn't always mean that we need to raise the score. Logically think about it. Estimation, this is something that you can do at home. Estimate the length of the wall of a classroom or bedroom or length of a car in feet, but try to do it without using things like rulers or yardsticks, okay? Figure out how to estimate without doing that. And let's do a couple of word problems. Josie wants to tile the floor, which is 12 feet by 8 feet wide. Each tile is $7.89 per square foot, and she thinks the cost will be about $315. Is that reasonable? So we need to estimate to see, is that cost close to what it needs to be? Is she going to be under budget or over budget? So we need to first think about how big is the floor? What's the area of the floor? So I do 12 times 8, which is 96. And then I think about how much it is per tile, and that's $7.98. I'm going to round that to $8. And I'm also going to round my 96 feet to 100 feet, just to make sure that I have enough floor tiles. So 100 square feet, $8 per square foot, we have about $800. So is the calculation reasonable? No, she is way off, and she will run out of money halfway through the floor. Richard is paid $11.85 per hour. About how much money does he earn in a year, 52 weeks, if he works 40 hours a week? Well, I'm going to do some rounding. $11.85, I'm going to round to $12. And 40 hours a week, I'm going to leave at 40 hours. That's a good round number. My 52 weeks, though, I'm just going to say, let's say he works for only 50 weeks. A good estimate for his annual salary. It's not going to be perfect. So that when we multiply all of these out, I'm going to do 40 times 50. Well, 4 times 5 is 20. Add 2 zeros, 2,000. Okay. And then I'm going to multiply by 12, and I get $24,000. I'm going to estimate that he makes about $24,000 a year. Okay, good estimation. Get in the ballpark. If you do too much rounding, too much estimating, then yes, your answer is going to be quite a bit off. But if you keep it to a minimal, reasonable amount, you'll be just fine. If you want some more practice problems of these type of questions, you can look here. Okay, and I hope this was helpful for studying and for your homework.